So the next question is going to be kind of long, and it reads, find the exact length of the curve y equals root x minus x squared plus arcsine of root x, okay? So arcsine is just another way of writing sine inverse. So let me just define that now. It's just another way of writing sine inverse, okay? So given a ratio of two sides of a triangle, you can find the angle, basically, all right? So they want us to find the exact length of this curve. So we're going to be giving ourselves a formula to use to find the length of this curve. And the formula goes like this. So the length of the curve, I'm going to write it A, is the integral, definite integral between interval AB of the root of 1 plus f prime of x squared. Okay? So this is the equation or the formula for finding the exact length of a curve. Okay? So we're going to be applying this formula to finding the exact length of this very complicated curve. Okay. So first of all, we're going to need to find y prime. All right. So let's try to find y prime. So the strategy here is to treat these as separate functions first, and just to derive this function and this function. Okay. So y equals the root of x minus x squared plus the arcsine of root x. Okay. So let's derive this first part. So I'm gonna, let's say, I'm gonna label this to be 1, and I'll label this to be 2, okay? I don't wanna keep writing out everything together. Okay, so let's do 1 first, okay? 1. So 1 is the root of x minus x squared, right? So the derivative of that, of dx would equal to, so this is a chain rule, so we have to evaluate the outside function first, which is the root. So we're going to move the exponent down, and then minus 1 to the exponent at the top, which would give us negative 1/2. And then we're going to derive the inside, right, which is the multiplication of this. So it's 1 minus 2x, okay? So that's the derivative of that. And we're going to simplify all this together. So we'll have 1 minus 2x divided by 2 square rooted x minus x squared. Okay, cool. Let's just move down a bit. Okay. So 2. All right, so 2 is a little bit more complicated, but we're going to get through this together. So we have arcsine of root x. Okay. All right, so let's put a y here too. Why not? So we're going to get rid of this arcsine because it's really hard to derive arcsine. So we're going to apply the sine function to both sides. So we got sine of y equals root of x. So this is a little bit easier. And now we're going to implicitly differentiate this equation, okay? So we're going to do d of dx of sine y. And we're also going to do d of dx of root x, okay? So this is going to be a chain rule again. So we're going to have the derivative of the outside function. So it's going to be cos, because derivative of sine is cos. So cos y times dy over dx, because the derivative of the inside function is just y prime, or dy over dx. We're going to also apply the chain rule here. So it's going to be 1 over 2 times x to the power of 1 over 2. Okay. Oops. Okay. Cool. So we're going to isolate for dy dx now. Okay. So we isolate for dy dx. We get so 1 over 2 times root x, and then there's also a cos y. Let me just get this. All right, so we're going to get 1 over over 2 times root x times cos y. Okay, so that's our dy over dx. But the problem here is whenever we implicitly differentiate, our derivative is a function of the independent variable and a dependent variable. So we want to get rid of this cos y. So we're going to use trigonometric identity here. So we know that cos squared y plus sine squared y equals 1. Okay, we know that equals 1. So we know that cos of y equals the root of 1 minus sine squared y. Okay, but we know that sine squared y, well, sine y is just root x. So sine squared y would be 1 minus x. And now we're going to sub in cos here. So actually dy over dx is going to be equal to 1 over, let me just see here, 2 root x minus x squared. Let me just see if this is right here. X minus x squared, yeah. Okay, so this is our derivative for our part 2. So overall, if I come back down here, so overall then, y prime of x, I guess you can say, is equal to 1 minus 2x times over 2 times root x minus x squared plus 1 over 2 times root x minus x squared. Okay, cool. And now we're going to simplify this all together, and we get 2 minus 2x. So 1 minus x over x minus x squared. You guys can go through this math by yourself. I'm just going to simplify doing all these other steps here. It's just a bunch of adding these fractions together and reducing the top and the bottom. So this is our derivative, okay? 1 minus x root x minus x squared, okay? Now we have our equation. So the length of our curve is equal to the definite integral of interval a to b of the function root 1 plus 1 minus x over root x minus x squared d of x, okay? Cool. All right, so let's recap what we did so far, okay? So to find the length of the curve, we're going to calculate the definite integral of this function. So what we did was we found the derivative of this original function by splitting it into 2 parts, I guess. You don't really need to split it into 2 parts, but I did it for, I guess, clarification purposes. And I found the derivative of both. I added it back together, simplified it, okay? But we're missing one thing. We're missing the bounds for this curve, okay? Now, normally, they would give you the interval for the bounds of this curve. They'll say, oh, find the curve, length of the curve from 0 to 4. They'll say, find the length of the curve from 1 to 100, okay? But here, they didn't give us the exact length of the curve, right? So we're going to assume that the length of the curve is the entire curve, okay? So let's look at this function, right? So what is the domain of this curve, right? So we can see that this function is expressed by the addition of 2 square roots. So we have the square root of x minus x squared, and then we also have the arc sine of root x, okay? So we know that for a fact that square root functions cannot be, the x cannot be negative, right? So in this value, this cannot be negative, so we're already restrained to saying, okay, x minus x squared, the domain for this part of the function has to be between 0 and 1. Okay. For example, if x was 2 or 1 or greater, then this x squared will be greater than this x, and this will be a negative inside the square root, and we don't want that, right? Because the square root of a negative number is a complex number, but that is not part of our function here, okay? So between 0 and 1, we're fine. Same thing with, I guess, -1, I guess, too. So actually, for this square root, it's between -1 and 1. All right, so that's the domain for this first part of the function, if you guys are following me, okay? We still have the second part of this function, okay? So arcsine, usually the domain for this arcsine function is -1 and 1. However, the domain is restricted to 0 and 1 because of the square roots, okay? Just like our first part of the function, we cannot have our square root have a negative number, right? And so because of that, our arcsine function's domain is, again, restricted to 0 and 1. And the general rule of thumb for finding the domain is we're trying to try to find the part of the function that is most restrictive, and the part of the function that is most restrictive will dictate what the domain is. In this case, the domain for our first part of the function, root x minus x squared, domain is between -1 and 1. I think. No, it's between 0 and 1. Yes, between 0 and 1. Because if this is a negative, then it would be negative minus negative, which would be a negative. So both of these functions, both parts of these functions have a domain of 0 and 1. So now we know that the length of the curve that we're trying to find is between interval 0 and 1, which is the whole entire curve. All right? Sorry if that explanation is kind of confusing. But usually finding a domain of a curve is not this hard, but this function is very complex. But conveniently, the domain is easily interpretable and understandable, I guess. If you guys want, you guys can pause this video and you guys can check for yourself the domain for this function. And you guys can see that the domain is in fact 0 and 1. It cannot be greater than 1 or less than 0, okay? So now that we have found our interval, we can write this down. So our interval is between 0 and 1, okay? So we're going to try to find this definite interval, right, of 1 plus 1 minus x over root of x minus x squared over dx, okay? Cool. So, so there's going to be a lot of computation here. We're going to expand this term first. So we're going to try to simplify our whole function in here because it can be simplified. So if we squared both numerator and denominator, we get this. 1 minus x squared over x minus x squared root of that dx. Okay? Which is, if we expand, we get 1 plus 1 minus 2x plus x squared over x minus x squared all over a root. Okay? We're going to include this 1 in here, so we're going to multiply this 1 by x minus x squared, and we're going to add it into our fraction here. So we get x minus x squared plus 1 minus 2x plus x squared over x minus x squared, okay? That's all rooted together. All right, pen in hand, right? So now we can simplify this quotient of functions, I guess you can say. So this would equal to square root of negative x plus 1 over x minus x squared d of x. Okay? We can keep going with this. We can factor out x at the bottom, and we can cancel out the top and the bottom here. So if we do that, we have 1 minus x over x, 1 minus x dx, and now we get this d of x. And if we now evaluate this integral, we get, so we use our power rule here, so we have to move, so it'll be x half or 1 over 2. of 1 and 0. Okay? And that equals to, we're almost there, guys, 2 root x of 1 and 0, which equals to 2 minus 0, and that equals to 2. Okay, cool. So let's recap everything, because it's a very long question. All right, so we defined the length of the curve to be the definite integral of this function here. If you guys want the proof to it, you just search in Google proof for the exact length of the curve, and you'll find it. It has to do with adding small increments of rectangles to a curve, and this is what you derive the function from that. So from that formula, we try to find our derivative. So our derivative is split into two parts, and we found the derivative of both, and we added it together, we simplified it. Then we had to reason the bounds for this function. So looking at the function, we had to find the domain, and conveniently, both parts of the function's domain is 0 to 1. So that means that the whole curve, the whole length of the curve is bounded from 0 to 1, and that's our interval. And by doing that, we found our definite integral by simplifying this whole complex function here and reducing it down to root of 1 over x, and then we calculated our definite integral, which gave us the value of 2. Okay, cool. So that's what the junior tutor also did. So they came up with the value of 2 in the end, so this solution is correct. Okay, cool. Moving on to